Hello, welcome to another lecture of CS360, and today we'll talk about the time hierarchy theorem. Okay, so the time hierarchy theorem basically says that if you had strictly more time, then you could do strictly more things with the computation. So in other words, a Turing machine with a certain time limitation can only do so much, can only recognize so many languages. If you increase the time limitation by more than a small factor, by more than like a logarithmic factor, then the time hierarchy theorem tells you that you will be able to do more things. There will be more things that you will be able to achieve with more time. So this is one of the few theorems we have that tell us that there's some computable languages that you cannot decide quickly in a short amount of time. We don't have very many tools to show you that, that a language that is decidable is not decidable quickly. We have, of course, some tools to show you that languages are not decidable, but it's hard to show this time-dependent issue. So the time hierarchy theorem is one way to do so, and one of the only ways we have. And so to formally state the time hierarchy theorem, we need to introduce this notion of a time-constructible function. So a time-constructible function is basically any function that sort of can just be computed within a reasonable amount of time. So let's talk about this. So time-constructible. So a time-constructible function, it's a function f. We'll just talk about functions that are actual natural numbers here, and it has to have a few properties. So first of all, just for technical reasons, we will want its growth rate to be more than linear, and in fact more than n log n. So we want f of n to grow at least as fast as n log n. Okay, and so we say this f is time constructible. So and then the other thing is so f here needs to be computable. By some Turing machine M. And then the main property we want is that basically M of 0 to the n outputs f of n in O of f of n steps. Okay, so essentially what's going on here is that we're giving M, the Turing machine M, a pretty easy task. We're telling it to compute f of n, not just given n as input, but given 0 to the n as input. What's the difference? The difference is that n, just describing a number n, that takes log n bits, right? But giving you n zeros takes n bits. And remember that when we count the running time, we always we count the running time in terms of the input size. So if we just try to describe a function which takes in its input size a number n and computes some function f of n of it, then that might have a certain runtime. Okay, but we're actually doing a much easier task. We're essentially doing an exponentially easier task. Instead of given a number n and outputting f of n, we're given 0 to the n, which is basically the same number n, but written in a very inefficient way, where the input size is exponentially larger than it needs to be. And then the task is to output the same f of n written in binary notation, so the same efficient representation of f of n as before. but this is like exponentially easier in a sense, right? Because we had a lot more input size to start with. Okay, so this is what we want. We want a machine which takes as input n zeros, basically, so an input of size n, and outputs f of n within O(f) of n time. Okay, and why is that important? It's basically this condition of within of n time allows us to use the function f as an upper bound on a computation, on the number of steps of a computation, such that if I want to simulate some input machine, somebody tells me, okay, simulate machine m for so many steps, for f of n steps, then okay, I will have to spend steps simulating m, but I would also technically, if somebody tells me simulate m for f of n steps, I would need to calculate f. And I want to make sure that this step of calculating f of n doesn't take more time than actually simulating a machine for n steps, right? So, or for f of n steps rather. So I want the part where we do the calculate f of n part. When we say, okay, we now simulate a machine for f of n steps, you're going to need to calculate f of n for that. But that should be cheaper than the actual simulation of a machine, right? So it should take you at most O(f) of n steps to calculate f of n itself. Okay, and that's the goal here. And so that functions f that have that property are called time constructible. Now it turns out that almost every function is time constructible. In fact, the first condition, the condition that f of n is omega n log n, this technical condition, this is the most binding condition, the condition that's most likely to go wrong. Everything else is sort of satisfied by all function that you're familiar with. So for example, n squared is time constructible, so is n cubed, and n to the any constant k. You know, for any k, that's a time constructible function. The bigger the function grows, the more time you have to output it. So it's sort of almost the easier it gets to be time constructible, the larger you go. So you know, 2 to the n is time constructible, and 2 to the n is time constructible. Very weird functions that are very complicated to compute might not be time constructible, but you don't have to worry about those. And sort of the definition of time constructible will ensure that we'll never worry about those. Also, the Beazy-Beaver function, even though it grows really fast, is not time constructible because it's not computable at all. So it can't even be computable within Beazy-Beaver time, because even though that's a long time, we know that the Beazy-Beaver function is not computable at all in any amount of time. So in particular, it's not even computable within Beazy-Beaver time. Okay, so there are some functions that are not time constructible, but almost anything you'll encounter is, so long as it grows at least this fast. So in particular, n log n itself is time constructible. And so is like n log squared n. Technically, we define time constructible to only be functional on natural numbers, so we're going to need to round it. Like, so for example, we could round this down or round things up. It doesn't really matter, but should probably round it to an integer so that we can ascribe the formal definition of time constructible to that function that required a function on integers, from integers to integers. Okay. Okay, so now we have this notion of time constructible. We can state the time hierarchy theorem. So let's state it. Okay, so this says, let's see here, the formal statement. It says that, so say that f and g are time constructible. And let's say that f of n grows slower than g of n over log g of n. Okay, this is little o, so strictly small. Remember, little o is like a strict less than. Okay, so then this class of time f of n is going to be a strict subset of time G of n. Okay, where the whole key thing, the whole thing to prove here is the strictness, this not equals. So the whole thing we're proving here is that time of n is not equal to time g of n if f grows substantially slower than g. In fact, if f grows more than logarithmically slower than g. Okay, so this is the time hierarchy theorem, and it basically says that if you had more time, like for example, here, imagine that f of n is like okay, like imagine f of n is n squared, and then g of n is n cubed. Okay, so then this is saying there are some languages that you can decide in n cubed time, but not in n squared time. Okay, by some Turing machine. Okay, and similarly, you know, if this over here is 2 to the n and this over here is 3 to the n, then there is a language that you can decide in 3 to the n steps, but not in 2 to the n steps. Right, so then with more time, you can decide strictly more languages, so long as the gap is kind of at least logarithmic between the two running times you're comparing. Okay, so let's prove this. So to prove this, we need to come up with a language that's in here, but not in here. And then we need to prove that our language has this property, right? So our language is going to be, well, to define the language, we'll first, we'll have this helper function h, and h of n is going to be gn over log g of n. Okay. And you can round that so that h is an integer. Okay. And then our language is going to be this language A here. It's going to be okay, so it's this weird language here that I'm writing. Okay, so what is this? This is a language of all, you know, description of a Turing machine. Okay, and then concatenated with just like k ones. We increase the input size by k artificially, basically. All right, so we're taking in an input Turing machine, but also plus k wasted space. We're going to put a 0 here before the 1 to the k, just so that we can know where the padding started, right? So we can take the input string and kind of read backwards until we find a 0, and that will let us know when this padding part started, and therefore what we should parse as a Turing machine. Okay, so this input, it basically looks like a Turing machine M plus some junk padding of length like k plus 1. Okay, and k can be anything. K can be an integer. And then what do we want? We will put such a padded Turing machine. We will put that in the language A if, first of all, the Turing machine rejects itself with the padding. Okay, it has to reject itself with the padding, but also it has to do so within h of this padded self steps. Okay, so it's h of its own description plus k plus 1, I guess, steps. Okay, and so you know, A will contain all strings of padded Turing machines for which this holds. Okay. So of course, for a single Turing machine M, A might contain some strings of the form M 0 to the k for some k, but not for other k, right? So for any given one Turing machine M, you may have different values of k here that causes the string to be an A, and some other values of k that cause the string not to be an A. Okay, so this is this wacky language A. We're now going to claim we want to claim that this is in time g of n, but not in time f of n. And remember that f of n grows strictly smaller than h of n. Okay, so h of n is g of n over log g of n, right? So by construction, f of n grows strictly smaller. There's like a strict inequality here. F of n grows strictly slower than h of n. Okay. So let's first try to claim that a is in time g of n. Okay. So why is that? Why would a be in time g of n? Okay. A is in time g of n because basically, well, we can take an input that so okay. So let's start with an input string w. So the first thing we can do is just kind of scan w to check whether it has this format, right? So we will kind of scan it from the end to see where the last 0 was. That will let us know where the padding is supposed to be, and then try to parse the rest as a Turing machine, and we can kind of do a linear time check to see whether the formatting of the string w is of the right formatting. And then if it is of the right formatting, so we are given, so otherwise, of course, so the wrong formatting we can reject. If it is of the right formatting, so we do have a string like this, then what we can do is we can actually simulate m. So we can simulate m, basically, m is a given Turing machine, but we can sort of act like a universal Turing machine and simulate a given Turing machine. So we're going to simulate this given Turing machine m on this input string, right? And as we simulate, we also are going to have a step counter. We will have a step counter that counts how many steps this simulation is taking, okay? And we will want to stop the simulation when it reaches h of this many steps, right? Like h of the size of w steps. So first we have to calculate h of the size of w, but we can do that within O of h of the size of w steps, because h is going to be time constructible. So I'm going to skip over some details here, right? We know g is time constructible. We do kind of need to argue from that, and we know f is time constructible too. We do kind of need to argue from that h will be time constructible. Let's skip over that. Okay, so we will calculate h on the size of w within OH of the size of w steps. And then we will simulate the machine m on w as the input. So w is this input here. We will simulate the machine m on w for this many steps. Okay. Now, how long does it take to simulate a Turing machine for t steps using another Turing machine? So this is actually not that trivial, because when we argued that you can simulate an input Turing machine, we sort of said, okay, you have your Turing machine on a tape, and you have to kind of go back and forth between, like, you have this Turing machine written down and has, like, the states of it are written on your tape, and you have the input that's also a string written on your tape, and you kind of have to go back and forth between the two, and make sure that you switch the internal states, put a marker on the internal states, and kind of move it around as your simulation of the Turing machine is proceeding. So we did not argue that you can do it fast. We only argued that it's possible to do so when we talked about the universal Turing machine. So we won't actually go into the details of this. It's kind of complicated to do on a Turing machine, but it turns out that you can simulate a Turing machine on another Turing machine for t steps. So t steps of the simulation using around t log t total steps. So the overhead is like logarithmic. Okay, and this is what we're going to use here. So we're not going to prove that. It's a bit complicated for how to achieve only logarithmic overhead. Okay, but this is possible. So we will achieve logarithmic overhead, and we will get that this total simulation on w, the simulation of m on this input w for this many steps will take h of size of w times log of h of the size of w, okay, which happens to be big O of g of the size of w, okay? So, it turns out that when h is this function g of n over log g of n, then h times log h is big O of g, okay? So Therefore, this is kind of a hand-wavy argument, but therefore we can, just by kind of directly simulating the input machine, we can decide whether the input string W is in A using only O of G of size of W time, and therefore A is in time G of N by definition. Okay, because we can decide it in O of G time. Okay, so that explains why A is in this wacky language A we defined. It explains why it's decidable in time G of N time if you believe that simulation can be that efficient for Turing machine. But it doesn't explain why we defined A like this, or why A is not in time F of N. Okay, so now we'll argue that A is not in time F of N. So let me just keep the description of A here and write that down here. So okay, so why is, we want to say A is not in time F of N, right? So suppose it was. So let's suppose suppose that A was in time F of N. So suppose, and then that means that we have some Turing machine. Let's call it M prime. So we have some Turing machine that decides A within O of F of N time, right? Okay, so now basically consider the input WK, which is going to be the string M prime 0, 1 to the K. So for any integer K, we have this string. Okay. And now so what happens when we run M prime on WK? Okay, so when K is large enough, so let's so here M prime is a fixed Turing machine, right? It's a Turing machine that decides A in OF of N time. So WK, when K gets large enough, then the length of WK is basically just K, right? It's K plus a constant. It's K plus a little bit, K plus 100 or whatever the size of this is. So it's K plus a constant, but it's basically up to this constant, it's just K. So, so that means that this machine, well, its runtime is O of F of size of WK, right? Which is basically O of F of K plus a constant, like let's call C this constant, okay? But we know that F grows slower than H, right? So what we know is if K is large enough, this is basically slower. Well, this F is just a little O of H, so we can do, this is a little O of H of K plus C, right? And so when K is large enough, what we'll get is that F is that the running time, right? So the running time, let's say that the running time, let's call it T sub K. This is the running time of M prime on WK. So when K is large enough, T sub K is just going to be strictly less than H of this WK thing, the size of WK. Okay, and that's because when K is large enough, you know, then this little O will start to kick in. This little O, which means strict inequality, will start to kick in, and therefore this F will start to be smaller than this H over here. Okay, so if the number of steps that M prime takes on WK is TK, then TK is less than H. Okay, but then what happens? If M prime accepts this WK, then WK will not be an A because WK is only an A if M rejects the string by definition. You know, the string is an A if M rejects. So if M prime accepts WK, then it got it wrong. But if M prime rejects WK, then by definition this WK would be an A, right? So M prime sort of has to get WK wrong for large enough K, right? Because this within H steps part, steps part will be satisfied for large enough k. So we won't have to worry about it anymore for large enough k. And once it's satisfied, then m prime can't get it right anymore. Once it's satisfied, then m prime, if it accepts, then it's wrong because it should have rejected. And if it rejects, then it's also wrong because it should have accepted. Okay, so A is sort of built on purpose so that Turing machines of running time less than h cannot possibly decide it. If they accept a string, then that string should have been rejected, and if they reject, this should have been accepted. So long as the running time is less than h steps. So that's the point of A. It's basically a diagonalization language, a language that kind of tries on purpose to fool every Turing machine, except only every Turing machine that runs too slowly. That runs into a little time rather. If a Turing machine takes a long time, then A does not rule it out anymore, basically, because of this within H steps part. Okay, and that's why we could show that A really is in time G of n. And that's it. So that tells us that A is not in time f of n, and therefore that time f of n is not equal to time G of n. So you can do strictly more things with more time. Those things might be kind of useless. A looks like a kind of useless language. Okay, but at least we can show something that you can do with more time. And what is that something intuitively? What can you do with strictly more time? What is A telling you to do in a sense? In a sense, A is telling you to take an input machine and simulate it, right? It's sort of like A is it's in a sense just trying to get you to run the universal Turing machine. A is telling you, given a machine, please just run it for k steps. Here, I'm giving you m and k, and just run the machine. Yeah, that's roughly what A is doing. It's a bit more complicated than that, but it's roughly what A is doing. And so it's telling you, okay, running a machine for so many steps. And essentially, the time hierarchy theorem says that if somebody's telling you to run a machine for k steps, you're not going to be able to do that in much less than k steps. Okay, so we can only prove that up to this log factor. That's a bit annoying, but generally this is the lesson here. Okay, that you cannot, what is it that you can do given more time? And the answer is you can simulate a given machine for more steps given more time, right? So there's no shortcuts to simulating a machine. This is kind of the lesson of the time hierarchy theorem. And there's also actually a space hierarchy theorem, which I won't go on in the video, but it is in the notes. It says basically the same thing, but just for space classes in terms of, instead of time classes. The proof is also just about the same. And the space hierarchy theorem doesn't lose the log factors, so it's a little nicer. And again, it just says, what can you do if you've got strictly more space? And the answer is simulate a Turing machine that requires more space to simulate. And there's sort of no shortcut. If somebody tells you to simulate a machine, there's no shortcut either in time or in space to just taking the amount of time that machine would take, or taking the amount of space. Like if somebody asks you, okay, here's a machine, here's an input, run this machine on this input, tell me if it accepts or rejects. You won't be able to tell if it accepts or rejects without actually taking that amount of time and that amount of space. Okay, at least up to this annoying log factor that's a consequence of how we proved the theorem. Okay, so that's it. That's the time hierarchy theorem. It's essentially the lesson of it boils down to the what I'm calling the motto of this course. The motto of this course is it comes from that poem. It says that you can never find general mechanical means for predicting the acts of computing machines. Or at least you can't find general mechanical means for predicting the act of computing machines any better than just running the computing machine, right? You can always run the computing machine. That tells you what it would do. But there's no shortcuts to doing that. There's at least no general shortcuts. If you know exactly what the machine is, if you happen to know that this machine factors a number, then okay, maybe you can find a better factoring algorithm. But if you don't know what the machine is going to do, you're just getting a machine as input. There's no general means that lets you simulate any machine. In other words, reading a piece of code, a fully general piece of code, and deciding what that piece of code is going to do, if you run it, That's not possible except for actually running it, except for tracing out the computation and seeing what will happen. And that's one of the main lessons of this course, really. All right.